Determine voltage V1 to V4 in the circuit of this figure under DC conditions. So under DC conditions, we know that capacitors act like an open circuit. So we're going to redraw this using drawing the capacitors as open circuits. You don't have to do this, it helps me. Okay, now the next thing that's useful to note is to see where is there actually any current flowing. So let's make a note of that, and that's only here. That's where current is flowing. So this was 15 kiloohms, this was 5 kiloohms, and this was 10 kiloohms. I'm also going to make a note of what's labeled plus and minus on each of the capacitors to make sure that when I give the voltages, I give them the right signs. And notice that the circuit on the right that I've highlighted, that is just a circuit with a voltage source and 3 resistors in series. So we can add those up in series and find out what the current is. So I can say that this is 15 volts. I can use Ohm's law. 15 volts equals the current times the resistance is 30 kiloohms. So divide 15 by 30K, and I get I equals 0.5 milliamps. All right, so now what you're going to be looking for whenever you're trying to find the voltage across a capacitor is to see, is it in parallel with anything that you can get the voltage of? And let's look first here at C4. C4 is in parallel with this 10 kiloohm resistor. So it has the same voltage as the 10 kiloohm resistor. So VC4 equals the same as V of the 10 kiloohm resistor, which is I times 10 kiloohms, which is 0.5 milliamps times 10 kiloohms, which is 5 volts. Notice I had the current going from top to bottom, so the top side is positive, the bottom side is negative, so that matches up. So we have, it is 5 volts and it is positive 5 volts. Okay, now let's look here at C3. The current is going in this direction. So we have a positive current, that means we're going to have a positive voltage for C3. And just like over here, C3 is in parallel with the 15 kiloohms. So VC3 equals V15 kiloohms equals I times 15 kiloohms, which is 0.5 milliamps times 15 kiloohms, which is 7.5 volts. Okay, next, notice that there's no current flowing through either of the resistors on the left-hand side, so you can ignore them.
They're just zero?
They're not just zero. This is 0. If we call this ground, this is 0, but the other side is not 0. The other side is not 0 because the voltage right here is not 0, and the voltage up here is the same everywhere. All of that has to be at the same voltage. So if this is ground and this is 5 volts, then the voltage right here is 5. And then as my current goes through that 5 kilo ohm resistor, there'll be a voltage drop. So 0.5 milliamps times 5 kilo ohms equals 2.5 volts. So I have, did I copy that right? Oh, this was 15.
Yeah.
15, thank you.
Use that first.
Yeah, that's 15. So, but there is still a drop of 2.5 volts, and so 15 minus 2.5 means up here I have 12.5 volts. So the difference between the bottom and the top is 12.5 volts. The top is 12.5 volts higher than the bottom. So this, we can say the bottom part's all at 0, the top is at 12.5. So C1, VC1 equals VC2 equals 12.5. You got to be careful with those voltages because they're sneaky. The currents, when there's no current flowing, well then current's 0. But sometimes there are some voltages sticking around that just don't seem like they should be there.
So to get, like, put 12.5, but 2.5 volts, where that?
The 2.5 was the voltage drop across the 5 ohm resistor
Oh, and then you subtract that
from 15,
I see.
right.
I see now.
Okay, for this one, we are supposed to reduce the circuit into a single equivalent capacitor. And we just need to remember that capacitors work the opposite of resistors. So notice that these two are series. So we can do product over sum. 6 times 12 over 6 plus 12, 72 over 18, which is 4 micro. I'm going to leave out the micro because they're all micro, and so we just know that we don't. It's not going to affect anything because we don't have any other kinds of units going on. Okay, so this was 4, and this is 6. Okay, well, the 4 and the 6 are now in parallel, so we can add them. Okay, now I have a 10 and a 10 in series, and if you have two identical capacitors in series, the equivalent capacitance is half. That's what you get from doing product over sum, but it is half. So that would be 5. Now I have a 3 microfarad and a 5 microfarad capacitor in parallel, so I can just add those.
Wait, did you explain the half again?
Yeah, it's just product 10 times 10 over 10 plus 10 is 100 over 20, which is 5. And it works that way every time. Okay, so now I have two 8 microfarad capacitors in series, And so just like before, you can do product over sum, or know that when you have two identical ones in series, the equivalent one will be half. So that'll be 4 microfarad.